Hello, we're glad you've joined us for this live webinar, What is Needed for Optimal Experimental Design and How This Might Be Taught to Laboratory Animal Scientists. I am Judy O'Rourke of LabRoots, and I'll be moderating this session. Today's educational webinar is presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. Let's get started. This is an educational webinar and thus offers free RACE continuing education credits. After the webinar is over, and to get your CE credits, click on the CE button located in the bottom left-hand corner of your web page. You can pose questions to the speaker during the presentation while they're fresh in your mind. To do so, simply type them into the Q&A box, which will open when you click the green Q&A button at the lower left of the presentation window. Questions will be answered after the presentation. To enlarge the slide window, click on the screen icon in the lower right-hand corner of the slide window. If you experience technical problems seeing or hearing the presentation, just click on the support button found at the top right of the presentation window, or report your problem by clicking on the green Q&A button at lower left. I now present today's speaker, Derek Fry, Faculty of Life Sciences, University of Manchester. Dr. Fry is a medical doctor and also a doctor of philosophy who has been interested in experimental design since including statistics in his medical student teaching in the 1980s. He continued that interest when he moved to UK government work, which involved assessing proposals for animal experiments in many different fields and advising on biomedical issues in animal-based research and testing. On retiring, he was granted an honorary position at the University of Manchester and has been running or helping run workshops on experimental design in the UK and various countries in Europe, Asia, and North America, and exploring how to teach the subject in an interesting and entertaining way. Dr. Fry will now begin his presentation.
Thank you, Judy. First of all, I should say that in this rather strained arrangement, you can't make these presentations as interesting and exciting as one can when you have an audience to react with immediately. But I should try and give you some questions as we go through. I was concerned really about how you taught this particular subject, experimental design, because I came across a lot of bad teaching. Now, the subject here is really not just experimental design in the broad scope, but also optimizing experimental design. And I think if you're going to think about teaching that, you've got to first think about what it is you want those who are being taught to actually pick up and take away with them from a presentation or a learning experience. And so therefore we're going to go through a lot of this in terms of working out what would be best to put in a course or a presentation or a series of lectures on experimental design which show how you can optimize that. And then we will think a little bit about how the teaching could be presented and what sort of results you might expect from that with different audiences. So to start with, let's have a look first of all about what might be optimal experimental design. And I do apologize for the bullet points at several points here. I have tried several different types of bullet points which have all come out as a T, not on my slides, but when it gets translated into the LabRoots system. So just watch for T's, think of them as diamonds or squares. Anyway, experimental design, optimizing, I think it would keep to ethical principles, and it should provide results which are valid, reliable, reproducible, and as widely applicable as possible. And that's quite a challenge, but also it needs to be efficient in use of animals and resources, and to minimize the impact of the experiments on the animals, that is, the severity, distress that they experience. So let's have a look at the ethical considerations. The first one is to think, is it actually worth doing the experiments at all? Does the sort of cost or severity that the animals experience, is that worth the sort of data you'll be getting out? And that's called a cost-benefit analysis, and it's one of the things that is worth putting in at an early stage when you're teaching experimental design. The next thing is to look at the classic 3 R's arrangement. That is replacing by using non-animal alternatives, reducing the number of animals over both the experiments and a series of experiments, and using the minimal severity procedures or causing the least harm or distress. And you may regard poorly designed experiments as unethical because they either use too many animals or not enough to show good results, or they use too much in the way of distress and harm to the animal for the results you're getting out. If they use too many animals, you're wasting animals for the end results that you're looking for, and if they use too few animals on each experiment, you're wasting animals by failing to show a real effect and needing to have other experiments to show that effect. So very quickly, the replacement ethical consideration starts with the question, is it necessary to use animals? And before saying yes, you should really think about computer modeling, in vitro possibilities, ex vivo possibilities like using tissue, and do a systematic review to make sure that the experiment proposed along the sort of lines you're proposing is actually necessary. I.e., you could ask, if I could not use live animals, what could I do? Or there's another way of doing it, and that is to say, could I alter the objective so that it was achievable with tissue culture or ex vivo material without using live animals during the experiment? But most of the experimental design thought pattern is about reduction or cutting down on animal use. And that can be achieved both by the design of an individual experiment, but also by the design of a program experiment, a series of experiments to a common aim. You can reduce by minimizing variability, and that's where consideration of good health status comes in, minimizing distress. And you can also reduce by collaborating across groups and making certain that the publications include all the elements that are necessary to repeat or judge the experiments that you're publishing. You can maximize the use of tissue across different groups, and in particular make available genetically altered lines. There is an element to which you would keep the numbers down by using the same animal more than once, i.e. reusing an animal. But clearly that adds to the cumulative stress of the animal if you're not careful. When you give groups a discussion about why they would design an experiment, the sort of results you get out are here. Obtaining valid results, knowing how widely those results may apply. Is it just to the particular circumstance of that experiment, or is it much wider? To use the resources, people's time, the animals, and the equipment efficiently, and to minimize the impact on the animals or the severity of the procedures, but also to ensure reproducibility. So those need to be in your mind when you're thinking about optimizing an experimental design, and therefore they need to be part of any teaching approach and be emphasized. And you can say that good experimental design calls for a combination of biological insight, which you need to formulate a good experimental question, and logic to work out a testable hypothesis around that particular question. But also an element of common sense to realize what you can do in the time or with the other constraints, and to plan accordingly. And right at the end of this comes the appreciation of statistics, because at the back of your mind you have to know how the results can be properly analysed. But in a way, the statistics comes last and the biology comes first. So if you're thinking about optimizing, you would think about formulating a clear objective, designing for minimal severity, designing for the results to be valid and the experiments reproducible, getting sequences of experiments that give minimum numbers and minimal severity overall, and getting the right numbers for each experiment in the program to achieve that. And the steps you might think of in designing an experiment were specifying the objective, formulating the hypothesis from that, deciding the best measures, considering how you would get the best effect, the biggest effect, and the least variability, identifying the experimental unit, and then planning the design or arrangement of experimental units around controls and experimental alterations within the constraints of the type of housing that the biological material is in, animals, fish, and that sort of thing. But you have to know how to arrange the allocation of units to get an efficient design. And in order to get an efficient design, you need to know how you will analyze those results. Into that, you will put certain ideas about what significance level or risk of false positive you will accept, and what power or ability to recognize a real effect you are happy with. And from those elements, you will estimate the group size for a particular comparison. And the problem about objectives is one that is sufficient to make it a key element of any teaching about optimizing experimental design, because unclear objectives are one of the most common failures. And only yesterday I was giving a group a task to devise an experiment, and the first thing they came up with was an objective which had 2 or 3 possibilities in it. You have to be clear about what you want and what is your priority in order to be able to formulate the experimental design properly. Because good objectives give clear hypotheses, and clear hypotheses lead to the best experiments. Have a look at this objective. Our objective is to determine how strokes can be prevented. Very broad, laudable, but actually very difficult to know whether you could achieve it or within a particular time frame, and how you would achieve it. What hypothesis are you putting forward? If you rephrase it as our objective is to test the reduction in stroke occurrence when a standard diet is supplemented with antioxidants, then you have a framework of a testable hypothesis. As biological experiments are comparative, you don't get a clear end result without a decent comparison. And to do that, you need to keep to certain fundamental principles, because if you don't, the results have a certain degree of uncertainty, and you don't know how much, and there is a bias that may be possible, and again, you would not be aware of it. And if those are there, you get unreliable results, you may get erroneous conclusions, and it may take a lot of other experiments to correct that, particularly if it gets into literature of a journal with high impact factor. So the fundamental principles are something that you would definitely put in any teaching program and think are worth emphasizing. And I would think the ones that are particularly key are getting appropriate comparisons. Usually you would have controls, and usually they would be concurrent. But you have to set them up so that they are appropriate and relevant, and there are cases when you can use historic controls as long as you have some concurrent ones. You also need to have several bits of the biological material in each of the experimental conditions. Because if there's only one, you don't know whether it's the biological material itself that's causing changes between two conditions or whether it's the conditions. And so you need a number of these so-called replicates in order to be able to detect a genuine difference between different experimental groups. But those replicates must be capable of being assigned independently to different experimental groups. And in doing the assignment, you have to randomize, because unless you randomize, you have the possibility of bias and you wouldn't know. But it is not just randomization when you assign to treatments or you select from a group. It is randomization throughout the experiment where there might be a bias that you are not aware of. And these fundamental principles all relate to a thing called the experimental unit, which is shown in some of the textbooks on experimental design, but not all. And it can be defined as the repetition unit, or that element of biological material that can be independently assigned at random to any of the experimental treatments. We'll look at experimental units a little bit later on, but first of all let's consider controls, because they are a fundamental way of checking that you don't get false inferences. Classically, you may consider them as negative or positive, internal or external, and concurrent or historic. Internal, by the way, is where the animal or experimental unit is its own control for a particular manipulation. For example, you take a baseline, put in a vehicle, and look at how that affects the baseline. You then put in your drug of interest, compare that effect, and then you put in the vehicle again to make certain the baseline and the effect on baseline has not changed. External ones are the typical ones where you do comparisons of groups of biological material. When you're doing a straight comparison, however, you don't need separate vehicle or sham-operated controls. One experimental treatment can be the control for the other, and vice versa, provided that is the objective, just comparing the two. And that can apply to different procedures, different strains of animals, different drugs, and so on. Essentially, the interpretation of your results is based on the relationship between the treated responses, whether they be controls or comparison responses. And some of the problems with the controls are effectively twofold. One is that you miss out necessary controls, and the other is you put in unnecessary ones. So again, as this is such a critical area, it's important to put it in any approach to teaching that involves optimizing experimental design. And to decide suitable controls, you need to think what the outcomes of an experiment might be, then think how you might interpret those outcomes, and then think what controls are needed to avoid misinterpreting. And in particular, there are occasions when you have to say to yourself, is a negative a genuine negative, or is it due to some effect that is masking the effect of the experimental manipulation. And for those sort of things, you might need a positive control to show that there is an effect in the circumstances when you think there ought to be. Randomization, as I've mentioned, is about making sure that you don't have a bias in the different groupings. So it makes sure that there is an equal chance of any inherent difference being in any one of your experimental treatment groups. So it avoids the possibility that the inherent differences get clustered and associated with particular treatments. Although, to be fair, that might be one possible random outcome, but the chances of that are very low. Also, you need to think about randomizing at every stage of the experiment, because in allocating the independent experimental units, it's relatively easy to see that there could be biases which happen to go into one group and give a false indication of the response of that group to the experimental changes. But there's also the problem that the observer or manipulator or the person giving injections gets better during the course of an experimental series or gets more tired and worse, and also that where you put the experimental units within the particular experimental treatment groups could be affected by the environment. Equally, you may get an effect of either skill improvement or tiredness in a series of measurements. So you should really be randomizing at each of those stages. And this is a fairly ancient set of work looking at an animal house and the effect of lighting on rodent caging within it. It's only really worth looking at the grouping on the far right, where you have got a light source which is in the ceiling. And if you have an uncovered top cage, you have a much higher lighting at the base of the cage than you do right at the bottom of the rack, where there is shading from all the other cages and where the amount of illumination has reduced considerably. So that means that going down a rack with illumination from the top, you will get different levels of lighting in the cage. And you can see some of the figures there, 250, for example, in the top right, 10 below it, and then right at the bottom, the figure drops to 3. That may not be a problem, but in species like rodents, which are more active at night than during the day, it may seriously influence your results because those in the higher cages may be showing adverse effects to the light, and those in the lower cages may be more active. So you have to take that into account, and this is why you would randomize where the particular biological groups and experimental groups are within the rack. Now, we talked about the experimental unit, and I gave you one definition. Here are a series of others. The unit of replication that can be assigned at random to a treatment, the entity, or a bit of biological material, that can be assigned independently to a treatment group. So there are two elements here, the random and the independent. And it's important to recognize that the experimental unit may not be an individual animal under quite a number of circumstances, groupings of animals or parts of animals or a pattern on animals may actually be the experimental unit. And in a crossover design, the experimental unit is the biological material for a period of time that is then compared against another period of time. And usually you're taking your measurement on a sample from the experimental unit. So let's give you something to think about. A researcher wishes to determine whether a drug protects against the effect of a mutation that affects late fetal development and produces observable effects after weaning. He or she proposes to randomly assign homozygous mutant females to drug-treated and control groups, then mate them with the appropriate males. The drug will be given during late pregnancy, the litters weaned, appropriately grouped, and the effects on the offspring observed. In that arrangement, what is the experimental unit? What would you think it was? Individual offspring, B, the cage, C, the female, and D, not sure. Now, LabRoots is going to give you a chance to give a response to that, and after a little while we'll close the poll, and I'll give you what I think is the response. I normally give about a minute for this in an assessment, which is not a serious assessment, but one that stimulates thought and gives a chance to consider the different options. So 10 seconds to finish that, and then if LabRoots can take it off, we'll proceed to what I think the answer is. Okay, can we now move on and see the slide itself? Because I would say what can be independently assigned to an experimental group or treatment is the female. And of course you can't assume that people are doing the best practice. I was part of a survey in Kilkenny et al. 2009, which got published, and looked at both sides of the Atlantic and papers from a number of journals, and found that those papers which indicated that they did random allocation of animals were really quite a small proportion. And those that actually blinded the person judging the result from the treatment that the animal had received were also a rather small proportion. Things have got a bit better since, and it doesn't say that they didn't, but it indicates that they didn't think it was important enough to put in the methods sections. And there is one particular study which looked at the abstracts of studies which might have given positive or negative results. And this was actually in a grouping for trauma scientists. And generally you would have thought there's a possibility of giving positive or negative results roughly equally. But if the randomization was not mentioned, there was a greater chance of the findings being reported as positive than if it was, and if neither randomization nor blinding were reported, again, there was an even bigger chance of positive findings being published in the abstract than negative ones. So there's a risk in this of allowing a bias to come in, which you don't see in the published work. And it's come out several times as people have been looking across different groupings and end results. One of the first ones was Perel et al., which are looking at the correlation between an outcome in animals and an outcome in humans. And the correlation was not good. This one by Scott et al. Was a very extensive study looking at what is published work of effects of different treatments on this particular disease, amyotrophic lateral sclerosis. But when they looked at all of them and assessed how they gave their results and the drift and patterns of them, they felt that most of them could be explained by the sort of natural variation, the normal noise pattern, rather than any specific effects of the agents. It's a very nicely controlled and looked at study and is worthwhile studying in detail. Similarly, MacLeod's group, there have been several publications from them looking at the how genuinely you can take published work in particular areas such as the stroke models, where small amounts of effect are clinically worthwhile, but there is a risk of bias which could substantially change whether you thought there was an effect or not. And because of this lack of randomization and blinding, several of these would be regarded as suspect. And more recently, you've had two papers looking at repeating landmark studies in-house. So these are across several types of discipline. The studies have been published, and what has happened in different pharmaceutical companies, they have tried to reproduce these in order to set up a drug discovery program, and found the degree of ability to reproduce them is really rather low. And they've decided that the probably poor design is a considerable element of this. That is not entirely without questioning, but it gives a good impression of the problems that arise if it is not clear that that has been a good design and that you can rely on the outputs. And the sort of problems you find going around and talking to scientists is that many don't know how to randomize properly. You don't just pick the first animal that comes in the cage, because that may be the one that is most anxious to bite you, or the one that can't run away faster. And you've got a risk also of biased results because of the way in which the studies were set out. And we've mentioned some of what is now a considerable literature questioning the quality of the studies. There is limited information on planning of the sequence experiments, and including some ideas about the 3 R's is really quite rare. Scientists that did have access to advice on experimental design, it came from statisticians, and of course they would be thinking about numbers, efficient design and that sort of thing, and not about what effect severity may have on the data or the loss of data points. And if you look at the sort of failings that you can see, experimental objectives unclear, poor hypothesis, you don't get the constraints, you forget that there's only a period of time that you can do things over, but you're going to take a period of time to actually get an output, and you may not have the technical capacity to get it within that time. The idea of getting the experimental unit correct is not one that comes into a lot of people's thought patterns. The controls may be missing out on key positives. You may not have the best measures to get the largest effect, and you may not have maximized that effect against the variability. Quite often inefficient designs are used, 2 group or more group comparisons when there could be a more efficient way of doing it, The sample size is often miscalculated. The units for measuring are sometimes not independent. Randomization may be done at some stage but not throughout. And there is a lack of realization of a possibility of observer bias. There's also quite a bit of incorrect analysis. Again, there's a number of published studies which have looked at the analysis and indicated that many of them are incorrect for the type of data they were getting. And finally, there is an element of incorrect reporting and presentation. Of course, not every experiment or experimental group has all of these. It's just these are relatively common as you go around looking at different experimental designs. And of course, none of those include this failure to actually go to the minimal severity. But this is an important element because good science depends upon good welfare. Physiological responses to suffering may change the data quality, consistency, or validity. And of course, we know anxiety, pain, fear, and distress can affect our physiology, and you would expect it to affect animal physiology as well. So you will get changes in heart rate, immune responses, and so on. And one of the things that you don't think about until it comes your way is the extent to which minor welfare problems can influence the reliability, reproducibility, and consistency of your results. But another thing about refinement, which is not really to do with the way in which you design, is that you do need to think about humane endpoints. Some time when you will stop the experiment or take the animal off experiment because the severity is more than you can justify from the results you're getting out, or because you have reached your specified objective and any further disturbance of the animal is not really justifiable, or it's become clear you will not get to that objective and you have to accept that any further suffering is not going to give you reliable data. And of course, taking animals off experiment may mean you've lost a data point, and you will need to take account of that in the experimental design. And the other problem about considering it experimental design and optimizing it as just reducing the numbers is you don't think about possible alternate objectives, you don't think about this effect of pain or distress, and you don't think about the variability that that may cause in the measure that you're taking, and hence the numbers that may be needed to investigate a real effect. But equally, the point about losing data is important because you need to avoid designs that would be highly sensitive to it. There's also the possibility of a conflict between reduction and refinement. Fewer animals, but more severity. Or do you go for lower severity and a larger number of animals? And the answer to the question depends upon the particular thing you're doing. You might, for example, accept the higher severity of the implantation of the cannula, where we're using fewer animals than you would need with the variability of taking several samples of blood. So the key elements in good design you might consider to be the objectives, maximizing the effect and minimizing variation, and getting an efficient pattern of your experimental units and experimental treatments. And of course, we've mentioned that clear objectives is not uncommon. We've done a number of workshops in which people have looked at the objectives in papers and taken the first or main experiment and try and see if they are clear as to what the experimenters were trying to show. And typically, we find approximately half the groups cannot find out what the objective of that experiment was. Probably more realistically, is the result that came from the Kilkenny et al. Survey, which is indicating that the objectives were not clear in about 5% of the cases. And of course you need clear objectives because you can't assess otherwise whether you need an exploratory experiment on a hypothesis testing one, whether you need animals, what are suitable controls, when it should be stopped because it's been achieved or cannot be achieved, and how to design properly. And one element we talked about in improving and optimizing experiments is to think closely about maximizing effect and minimizing variation. In the first case, you can increase the signal, give a larger stimulus, use more sensitive subjects. In the second, you can decrease it by improving uniformity or standardizing or doing a covariate approach. Or you can improve the experimental design so some elements of variability can be excluded from the comparison between the experimental groups and their variability. If you can't do that, you're stuck with increasing the sample size. So this is one element that it would be key in looking at how you teach to optimize experimental design. And when you look at the sources of noise or variability, those are the sort of things you get: age, sex, species, strain, health, time of day, training. And those are just the animal factors. There's also human factors and environmental factors to consider. And you can think in another way of classifying this. What affects the experiment is who does it, or who is associated with it, what is the arrangement, and where is it taking place, and when are you taking the samples or doing the experimental manipulations. And it's important to look at variability carefully, because if you look at a standard measure for variability, the standard deviation, into the circumstances I've given on the top right for a two-sample comparison, in these particular circumstances, a standard deviation, as you can see from the graph, would mean a group size in each of the two experimental groups being compared of around 8. As you get a larger standard deviation, your group size goes up. As you get a smaller standard deviation or variability, the needed group size goes down. But if you look carefully at the group size for 0.6 on that graph, you see that there's around 20 animals per group needed. If you drop that to 0.3, it's only 5. So there is a squared effect between the variability and the number of animals you need to do a two-sample comparison. And a similar effect is seen in a more complex design, whereby you have a 2x2 factorial experiment. So the last thing to think out and to make certain is included in some form of approach to optimizing experimental design and teaching about it is to match the design to the experimental question as well as getting the right group size. And again, that particular survey indicated that where you could use factorial experiments in which you can gain more information from the same number of experimental units, only about half or less of the papers actually took to using a factorial design when there was a possibility to do so. And this is a way of wasting animals for the amount of information you can get out. To classify them, you can think of a fully randomized design, of which one of the uses is a two-sample comparison we've talked about, or you might have several sample comparisons, experimental group comparisons. Another is a randomized block. Factorial, we've mentioned, it tests simultaneously different factors and their effect. repeat measure is when you use the same biological material over several periods of time. And sequential is when you do a series of small experiments and the ones further down the series are informed by the earlier ones. It's only possible if data is attainable reasonably quickly, and you have to be careful that there is no time trend so that the later ones are affected by some bias according to the time in which they are done. But provided that's done, you can get a very good minimization of the use of animals to a particular objective. The important thing, though, is to make quite certain that you set stopping points beforehand. So you don't just carry on until you find out what you want to find out. Anyway, the advantages and disadvantages are shown briefly here. The fully randomized design and two or several comparisons is well understood, but it may not be the most efficient. The randomized block enables you to take out certain elements of the variability from the comparison between experimental groups, and the Factorial gives you information on more than one thing within the design, and it shows the interaction between those elements, but it can get very complex. You have to be careful in a repeat measures design that there is no crossover between the different time periods, and in the sequential design you've got to be very careful you don't have a bias. And we've mentioned a number of terms. Factor is simply a discrete characteristic or source of variability, and typical factors are the treatment, the experimental manipulations, controls, drug treated, and so on, the sex, a strain, the litter that an animal may have come from, the diet which is given, or the day in which an experiment was set up. All of those can be regarded as factors. And blocking is simply grouping according to a characteristic or source of variability. And it's worthwhile in certain circumstances. We've mentioned power, and I've given an indication that it is crucial to decide what are the chances of getting a genuine result, a real result, when it really exists there. This is a typical randomized block design for an animal studies. You can block or group according to age or parentage or that sort of thing. This one is done by time, and you have 4 time periods, and you accept that you will not get all of the experiment done in one of them, but you will be able to do the 4 different surgical treatments during that time period. The important thing is, A, to make certain that every one of the treatments being compared is within the block, in this case the time period, and that they are randomly arranged within it. And that's a pattern that would fit. This is also called a stratified random arrangement. And another illustration is, supposing you picked up a series of relatively newborn pups, you have weaned them, and then you put them on different diets. If you just take a group at random from a whole collection of animals, you might get those sort of results. If, however, you knew the parentage of the ones you picked up and were able to indicate those in each of the outputs, you might find that in the red litter 1, all of the diet B results were below the diet A. In the clear circles coming from litter 2, you would get, again, all of the diet B1s below diet A, and similarly for those from litter 3. And that means you get a fairly good idea from that there is an effect of B against A, whereas you didn't when you were not aware of the parentage they came from. Factorial experiments are essentially trying to get more information from the same experimental units. And they do it economically, and they show how general findings are. They spread it across several of the factors. Effectively, you're doing more than one experiment within the same time period. And if you want to think of it, you can think of a single factor experiment as a two-group comparison between treatments A and B. And if you wanted to repeat that in two strains, that's the sort of pattern you have. You'd need twice the number of animals. If you do a factorial design, you then find that you have both the strains within each of the treatment groups. So for each treatment, you have 8 experimental units. For each strain, you have 8 experimental units, but you've only 16 altogether. And in these sort of experiments, because you're estimating the biological variability from the whole of the experiment, the individual experimental groups, in this case, say strain 1, treatment A, can be quite small. Here, although you have only 4 in each strain treatment combination, there's 8 for each treatment, and 8 for each strain, and 16 for estimating variability. Although because of other constraints, you don't get all the 16, 15 degrees of freedom. But the key thing about these type of designs is they show interaction between the 2 or more factors, and therefore they are the good way of optimizing your output. It's particularly true when you're looking for combinations, say, of age and drug dose in a series of experiments where you're looking at a drug's mechanism of action. They show you what is the optimal combination. So, to summarize, I think that to optimize, a researcher needs clear objectives and testable hypotheses, a good understanding of how to obtain valid, reliable results, adequate and appropriate controls, correct identification of the experimental unit, and an avoidance of bias. But they also need the skill to select an appropriate and efficient design and an understanding of how to minimize severity. And the way to bring this across in teaching is not just by presentations like this, but by also including some elements of problem solving, identifying the experimental unit as we did in the course of this, but also looking at what controls you'll need in certain scenarios, looking at designs which are faulty and seeing if people can pick those out, and also allowing them to select from a series of possible designs for ones which are appropriate for a particular scenario. And you use a facilitated discussion to bring that out, and also to think about the impact on the animals and how you might minimize it. And by questioning people, you get them to think about what they would do and to make a decision. And that reinforces the key points, although it has to be done without causing them embarrassment or distress themselves. And that's where we'll end for that and give a chance to come back on any of the points. Thank you.
Thank you, Dr. Fry, for that presentation. So a quick reminder for our audience on how to submit questions. Simply type them in the Q&A box found by clicking on the green Q&A button at the lower left of the presentation window. Dr. Fry will answer as many questions as time permits. We'll give you some time to formulate questions.
Is it possible to show the results of the poll on experimental unit at all?
Yes, I believe we can show that. There we go.
That's interesting, isn't it? Only about half of people have picked up the female. And that's about what you might expect from looking at papers. Quite often people have not picked out the correct experimental unit, and you can see it from the published paper.
Well, if there are no questions today, I would once again like to thank Dr. Derek Fry for his presentation. Do you have any final comments, Dr. Fry?
No, I think we've covered rather a lot. What I haven't done is talked about different teaching methods, but those are so applicable to the local circumstances that it's quite difficult to generalize.
Okay, well, it was wonderful. I'd also like to thank the audience for joining us today. This is an educational webinar and thus offers free race continuing education credits. After the webinar is over, and to get your CE credits, click on the CE button located in the bottom left-hand corner of your web page. This webcast can be viewed on demand through August 4th, 2016. LabRoots will alert you via email when it's available for replay, and we encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.
Thanks very much to LabRoots.
Oh, you know what? We have a question here. Oh, we have several questions. Would you have time to answer some questions?
Well, we've got 4 or 5 minutes, and I've got a bit longer.
Okay, so let's see this one. Let's see. Besides a statistician, what other subject matter experts would you suggest consulting?
Usually with regard to severity, and sometimes with regard to what can be done without animals, the local vets can help. And most places have some vet that will come along to deal with the laboratory animals, and they are getting better at thinking about design as distinct from just what the severity is.
Okay, well, thank you for that.
If not, it's worthwhile asking different experimenters, and there are a fair number of sites now. Go3R, for example, gives some idea of severity as well as other adverse effects.
Great. Okay, well, I see that a number of people have written in to ask about copies of the presentation. So I'd just like everyone to know, for a copy of the presentation, it will be available for downloading later during the on-demand period. So
yes, I haven't been able to do a summary set of these yet, but we'll do by about this time tomorrow.
Okay, great. And as we said, the webcast, the on-demand period, extends through August 4th, 2016. So again, thank you, Dr. Fry. Thank you to our audience for joining us.